Hello everyone. So at this point, we've become masters of endpoints and writing an application that can transmit data from a server to a web page and then load that content in the web page using browser APIs. From this point forward, these lectures are going to shift gears a little bit. Now that we know how to transport data, our next major topic is going to be about the most common mode of persisting data, so that it's permanently stored even if we have to shut the server down. And the tool for this is what's called a relational database. We're going to look at various types of queries that we can pose to a relational database and see how we can integrate the responses we get back into our web server's available endpoints. So this is something we'll be doing over several videos, and we're only getting started today. In this video specifically, what I want to cover is just a little bit of information about modeling our data. So we're going to look at how we can break down all of the data we have to store into entities and relations, basically things, and how those different things are related to one another. One of the big topics when we're doing this is discussing the cardinality of a relation. Basically, how many of one thing relates to exactly one of the other thing. And thinking about this is going to have a big impact on how we design our database and what tables we create. We're also going to look just a little bit at how relational databases help us represent and access our data. We'll talk a little bit about the keywords that we're going to be seeing, and I'll leave you off with a roadmap of where we're going from here. So with all of that said, let us begin. So far, when we've been writing our web applications, we've mostly ignored the persistence question. We've maybe used a file to load things in, done a couple simple examples like that. But if we're designing something that we want to be production ready and have real users use, it can be helpful to break our application down into some layers. We've got some data that we want to represent, and at some point, all of that data needs to be persisted. So it's useful to think about, how does this model of different objects that I've got actually fit onto a disk? What is the information that I need to preserve, and what formats will allow me to save it to a file or put it somewhere that I can retrieve it later? When we're in code, we're thinking more about a logical data model, a way that we can break our different fields into objects that are part of classes. And the big goal here is thinking about, how do we transmit things from one part of a program to the other, usually passing them between functions? What is the convenient way to break things down for that? Similarly, if we're talking about getting things from the client to the server in a request, or from the server to the client in a response, we also need to be thinking about our transport data model, something that can encode that information in whatever protocol we're using. If you remember, when we talked about HTTP, this became relevant because when we make a fetch request, everything has to be serialized as text. We even called JSON.stringify when we were in the browser. One of the important things to note is that our needs might actually change from layer to layer. It might be the case that we've got this one monolithic file with tens of thousands of records, each on its own line. And when I read that in from my persistent data model into my server code, I break that up and split off each line into its own object. It might even be the case that that one line gets decomposed into multiple objects. Maybe there's some duplication in the file that isn't necessary in the code because we can take references. Similarly, going from our server code into our transport, our endpoints, we might decide only some of the attributes on each class should be represented. Maybe there are things that we can't encode as strings, like lists of other objects, so we decide to just exclude them from our transport data model entirely. This is the reality of working with this layered data where we're storing things separately from how we're coding them, separately from how we're transmitting them. And developers tend not to like to have to keep many things in their head at once. So what we prefer to do is create one unified model that just shows in the abstract how all of these different concepts are related. There's actually a tool that helps with this, what is called the Unified Modeling Language. And the Unified Modeling Language is just a set of rules to help you design visual diagrams of how the different components of your data model fit together. In UML, each thing that you're representing is what's called an entity. And we represent these entities with boxes. One easy analog here is each box is sort of like a class from an object-oriented program. We've got a name for this thing, like I have this example here, which is a course. And then beneath that in the body here, we create a list of the details that that one thing has. Like our course might have a course ID, a name, and a meeting time. These are sort of like the attributes of that class, the fields that each object gets its own copy of. It turns out there are analogs for this in our other layers as well. When we're writing our transport, our web API, this is sort of like one endpoint and all of the details we get back on one endpoint. Once we start working with databases, we'll even see this is sort of like one table and all of the columns that are part of a table. And that's what's really convenient about this UML model, is that it works roughly the same for any of these different layers that we're working in and writing code for. So this is one entity in the model with the attributes that are part of that entity. However, the other big component of the UML diagram is how different entities relate to each other, how one thing is connected to another. To represent that in UML, we draw a dashed line between our two related entities. And the way that we draw the line actually communicates a little bit more about how these two things are linked. So if we just draw a plain old line connecting one entity to another, we're saying that there is just a one-to-one pairing here. A great example of this is something like our course from before linked up to a final exam. Every course has one final exam that usually has the same number of questions for everyone in the class. It's got the same start time, the same due date, same number of points possible. So if I were representing these as different objects in my code base, every course should have exactly one exam, and every exam should hopefully only be used in one course. Otherwise, why is this being treated as two different courses? So often these one-to-one pairings, if you have a relationship like this, the one thing to look for is checking whether these are actually distinct. Here in this case, course and exam are definitely distinct. They're two different concepts. It makes sense to partition them like this. Occasionally, when you have a one-to-one pairing, you might end up realizing if you draw it out like this, that you're representing two halves of the same single thing and maybe they get merged together. But this is our simplest form of relation here, saying one of thing from group A belongs to exactly one of thing from group B and vice versa. They are unique pairings. Our next type of relation loosens the grip a little bit. If many instances of one entity can all be linked to the same instance of its target, then what we use is a many-to-one relation. A many-to-one relation is great for representing groups of things. An example here is we've got a playing card, and every playing card knows things like its suit, its value, and then we've got a deck of cards. A deck of cards might know about things like a manufacturer and the backing image that's on the back of every card. But this one deck needs 52 playing cards. All of those playing cards can only belong to one deck. We can't have it be in two places at once. So this many group of cards is each linked to one deck, and that's where we get that many-to-one relation. The way that we represent this in UML is by putting a little crow's foot on the side that branches out. So because we have many playing cards, we put that little crow's foot there to demarcate that there might be more than one that are linked to the same thing. In code, we often represent this with a list. Our deck object would have a list of card objects inside of it. Sometimes we might also represent it with a reference, where each card has a reference to the deck that it belongs to, its parent deck. Those are equally valid in code, but one interesting note about databases is you're going to be much more likely to see this representation here, saying who is the parent of this, what is the one thing that this object is linked to. So keep that in mind, because that's going to become relevant in just a little bit. But this many-to-one relation is kind of the most common that we see in databases. It's great for saying things like, here is a user and here are all the things a user has done, all of the posts they've made, or all of the items that they've ordered in their shopping cart, or all of the different actions that they've done as they've navigated through our website. Many-to-one relationships are flexible enough to represent a history while still constrained enough that we can find the stuff linked to something pretty quickly if we know that parent. When that's not enough, we also can build out many-to-many relationships where both sides can store multiple references to things from the other. So if we bring back our course example, this is sort of something like the relationship between a course and a student. When a student signs up for classes every semester, they usually sign up for more than one, so that one student might appear in 5 different courses. Similarly, courses only run if they have a bunch of students registered, so each course might have a list of 25 students in it. Both sides here now have a list, and that's a problem, because what we just said was databases don't really like lists. We don't have good access to a collection type at all. So what we normally do when we have a many-to-many is we decompose it down into 2 many-to-ones. Anytime you see a many-to-many, you can represent that same exact relationship as some third thing that links together the other 2 sides. In this case, now each course has many registrations, but any given registration is this one student and this one course, they are linked together. Student can have many registrations, but again, each one of those registrations is just mapping one pair of things on either side. And the benefit here is in a actual application in the code that you write, you can still use lists, but in a database, you can use this third thing as another table. And what's really nice is sometimes you start to realize there's extra information here that's valuable to pull out. In this case, things like maybe the term someone registered for the class or the final grade they got in that class. You can store this extra information on this third entity in the middle, and it will mediate so that you don't have to store bunches of things on both sides, because that can make it really complicated to bounce from one side of your model to the other. So those are our three types of relations: one-to-one, one-to-many, and many-to-many. You can also do many-to-one versus one-to-many. Some people consider flipping them as two separate things, but this is the cardinality of a relation, and it is the biggest thing that you have to think about when you're figuring out how to break down the data you have to store into tables. So this is relevant if you want to use a relational database. The entire reason I am showing you these diagrams is because from here on out, we're going to be working a lot with relational databases. Relational databases are just tools that specialize in storing and retrieving data using what's called the structured query language. This is a pretty concise, declarative language that specializes in writing really complex questions. You can do things like say, get me all students who registered for a course in the fall, whose name begins with John, who registered for more than 4 classes. Write that in a single statement in structured query language and get back just a table of results. So it's an invaluable tool for a lot of what we do in web programming, which is allowing users to ask for and filter different entities that they want to retrieve. So there are many different databases, and each one of them has its own little dialect of SQL. It's a standard, but not strictly a language. Someone has to make an implementation of it. So in this class, the version of SQL that we'll be using is Postgres. Postgres is open source, and it's pretty close to the ANSI SQL standard. So most of what I teach you in these videos will be applicable no matter what relational database you use in the future. The one other note I have is that you may have heard of technologies like NoSQL. These extra tools don't follow all of the strict rules of our relational databases, which makes them great for just storing and retrieving really simple queries about data. But the relational data model has stood the test of time. It has stuck around for decades. So the focus in this series is going to be relational databases, because if you can understand and follow all of the principles here, picking up a NoSQL database in the future will be much, much easier for you. The last thing that I want to leave you with is kind of a mapping, a lay of the land of this structured query language. So in SQL, every statement declares an operation that you want to do to the database. And usually it's in the general form of an action on some target with some details. So in SQL, this roughly maps to all of the same CRUD operations that we did for our endpoints: creating, reading, updating, and deleting. If you remember with endpoints, we had HTTP verbs that let us communicate this, like get when we wanted to read some information, or post when we wanted to create something, put when we wanted to update it. In the same way, pretty much every SQL statement that you write will start with a verb, and there are 2 sets of these verbs. There's one set that deals with data definitions. This is what we use when we're creating a table or creating a column, changing a column. It's what's called the DDL operations in SQL. And for pretty much every flavor of database, when you want to create a table, for instance, you put the word create, you put the word table, and then you put the name of the table and all of the columns in it. If you want to change a column, you put the word alter, you put the word column, and then you put the name of the column, the table it belongs to, and what you're changing it to. Same thing if you want to delete a table, drop, and then a table, and then the name of it, and so on. Similarly, if we want to manipulate the data, not change the structure of it, but instead change just one row, one piece of information we're storing, there are data manipulation keywords in SQL. Most of what you do with a database is ask it questions. You ask it questions by putting select, and then the table that you're selecting from, and then whatever fields you want out of it, whatever conditions you have on it. Similarly, we've got actions for inserting, updating, and deleting data. It's going to be several videos where we cover each one of these, but just conceptually, it can help you understand where we're going from here if you try to break it down and think about SQL just in this sort of structure of, well, which operation am I doing and which type of thing am I affecting? The DDL operations for the structure of your data, or the DML operations for the actual data itself. But with that, I've covered everything I wanted to in this video. We've looked at the UML model and seen how we can think about our data as it is being preserved and persisted on a disk. We've talked about the relationships between entities in UML, how we can classify them as one-to-one, one-to-many, or many-to-many. And we've gotten a little preview of SQL here, seeing some of the keywords that we're going to look forward to over the next couple of videos. In the next video, we'll be taking a look at specifically creating tables, this first operation here, how we can connect to a database and create our model inside that database. So I look forward to that, and I'll catch you all in the next one.